Hi, I want to talk about radioactive dating. Not really toxic relationships, but how we can use the rate of radioactive decay as a way of aging different materials. Now, with nuclear physics, the time between radioactive decays is probably one of the closest things to a random number that we can get to in physics. But, given enough material, we can characterize the average likelihood of radioactive decay events happening, and usually that characterization is in the form of a half-life. The approximate amount of time that it would take half of the possible radioactive decays to occur. So the way that radioactivity works, the rate of radioactivity, which is the derivative of the number of radioactive particles that we have with respect to time, is equal to minus a constant times the number of radioactive particles that we have. So this is an exponential decay process. So the number of decays that we would see at some point would be equal to the original number of radioactive materials, or the number of decays we have remaining would be equal to the original number of radioactive particles we started with times Euler's number raised to minus a characteristic value lambda times time. So to figure out that characteristic, if I have half of what I started with, then 1 over 2 would be equal to Euler's number to the minus lambda times the half-life, the time to get to 1/2 of the original particles. So solving for lambda or solving for the half-life, either way, we would end up with a ratio. The half-life would be the natural log of 2 divided by that characteristic lambda. Lambda would be equal to the natural log of 2 divided by the half-life of the radioactive isotope that we're dealing with. And the rate of radioactive decay, since it's based on the number of decays that we have, would be equal to the original rate of radioactive decay times that exact same exponential decay dependence. Now, there's several forms of radioactive decay that we tend to use in aging things in physics. One is with radioactive decay in uranium, which is usually used to identify the age of things like rocks, but for organic material, particularly things involving humans, we tend to use radioactive carbon dating based on the presence of carbon-14. Now, carbon-14 is something that is generated in the atmosphere due to high-energy collisions that are happening. On average, there is a typical ratio in the atmosphere for carbon-14 isotopes compared to carbon-12 isotopes. And that ratio is approximately 1.3 times 10 to the negative 12 carbon-14s for every carbon-12 that we have. Now, the half-life for carbon-14 is 5,730 years. So say we find an amount of material, like a campfire, and we want to figure out how long ago that signifies some form of human presence. Well, we could take a small sample of the carbon from that ash and measure its decay rate. So, say we measure the decay rate and we're observing 250 decays per minute. And we have a 25-gram sample of carbon. Well, we would want to figure out how many carbon-14s we started with to figure out our original rate of decay, because the original rate of decay would be lambda, the natural log of 2, divided by our half-life, times the number of carbon-14s we started with. So to find the number of carbon-14s, if we have 25 grams of carbon, there are 12 grams of carbon per mole, so that means we would have just a little bit over 2 moles of carbon. We'd multiply by Avogadro's number, and then multiply by our ratio of carbon-14 to carbon-12. In terms of an original decay rate, well, we'd multiply that value by the log of 2, And then we divide by our half-life in minutes. So we would take 5,370 years, multiply it by the 365.24 days in a year, times the 24 hours in a day, times the 60 minutes in an hour, and dividing that into our numerator, we get an original decay rate of 375 decays per minute. So, if our current rate is our original rate of 375 decays per minute, times e to the minus natural log of 2 over our half-life, times the amount of time that's elapsed, then we can find the amount of time that's elapsed by comparing the ratio of rates. So the current rate compared to the original rate is right around 2/3. So the time would be minus 1 over lambda, so we'd have minus our half-life divided by the natural log of 2 times the natural log of 0.667. And when we multiply that out, we get a time of about 3,350 years ago. Thanks for watching.